In this video, we're going to talk about scale. Scale is an important element of understanding how you're working in the Cartesian plane because it's almost like units when you're dealing with word problems. It tells you how much each thing is worth. So here we're on page, let's see, this is page 4 of your unit book. And you see about partway down the page here, it says scale, and there's a blank for you to fill in. What I want you to write in this blank on page 4 of your unit book is a definition for scale. It's kind of a vulgar definition that we're going to put in. It's not really a very formal mathematical one. But what I want you to write in is something along these lines here. You would say, let's type this in. We'll say that scale is labeling numbers along each axis that tell you how much each box is worth. And when I say box, that's not a very formal mathematical term. What I really just mean is how much each jump means here. Like if you look at this example here, you see that each line on the y-axis represents 20 millions of rentals. Okay, the millions here is telling us just that each of these isn't just 20, it's 20 million. And then along the x-axis here, you can see based on these numbers showing up in all these notches that each notch represents 1 year. It's starting with 1986, then it's jumping year by year by year, and then gets to 1991, and then another 5 years to 1996, and so on. Now this kind of graph that you're seeing here is the kind of graph you've probably seen in history class. You might have seen it in science class as well. These are very useful graphs, but there's an important thing you need to understand that's different from how we'll deal about graphs in math class. This one here, you see this squiggly line down here. You've probably seen this in other classes. A lot of you know what that means, that squiggly line. That means that we're actually jumping from 0 to a number where it starts to get significant, right? We're not showing all the numbers from 20, 40, 60, 80, 100, 120, 140. We're going straight to 160, right? The same squiggly line is showing up over here. Also, we're not starting at the year 0. We don't care about number of video rentals during the Roman Empire, right? We're starting at 1986 and we're moving along from there. So this makes a lot of sense when you're talking about economics, when you really just want the graph to represent where there's significant numbers showing up. There's no point in showing all this empty space that would go from 0 to 140. This graph would only start to get interesting around 160. But in math, we don't want you to do that. And there's a good reason why we don't want you to do that, okay? Because in math, the Cartesian plane it works like a visual calculator. You'll see it has some interesting properties. But the calculator part of this graph in the Cartesian plane doesn't work if you break the scale. So that just means no squiggly lines in Sec 2 Cartesian plane math. You'll see there are other things you can do safely with the scale, but you cannot break the scale, which means jumping from 0 to some number that you'd like. Okay. Now, what I want to warn you against is a few misconceptions that people have about scale in secondary 2. One of them is that they assume that because your scale has to be consistent, that you can't break the scale with those squiggly lines. We know that means just that each box has to be worth the same. You have to start at 0, and then each box, if this first box here, if this first jump is worth 1, because I see the number 1 here, that scale here, this number here is telling me this box is worth 1, then each subsequent box also has to be worth the same amount, right? These numbers are jumping by a consistent amount. That just means I'm not breaking the scale. However, it is okay, like you see here, it is okay for the jumps along the x-axis to be different from the jumps along the y-axis. Each of these boxes here on the y-axis, you see I'm jumping by 5 every time. I'm consistently jumping by 5 every time. I don't start going from 0 to 100 and then 105, 110, 120 or whatever. I am always jumping by 5, but the jumps by 5 here are different from the jumps along the x-axis. That is okay. You are allowed to do that. There's no squiggly lines, there's no breaking the scale, but you are allowed to have a different scale on the x-axis than you do on the y-axis. All right, now let's look at some common mistakes that people make with scale, right? We already talked about what scale is. Here's another definition. It's really the little numbers that tell you how much each box represents, is another way of thinking of it. And like I was saying before, you can have one scale for your x-axis and another for your y-axis. They're allowed to be different. Typically, and most of the time, the ones you'll see, they'll be worth the same, but that doesn't have to be the case. Okay, so here's a couple of examples of some scales that follow the rules, that are good. If you look at this one here, This is a pretty common scale you'll see. We'll see this in a lot of problems where you've got an x-axis here and a y-axis, and the way that the scale is labeled here, you can see these numbers. Each box here is worth 1. We're jumping from 0 to 1 to 2 to 3. Since negatives show up on the left of the axis, we have the same jumps, always of 1 going this way, right? So from 0 to -1 to -2 to -3. And likewise for the y-axis, we see that each box represents 1 here. This is a good scale, pretty straightforward scale. You'll see this a lot of the time. It's kind of hard to see that there are negatives here, but this is -1, -2, -3. Note that the numbers here are always, like on the y-axis, they're always to the left of the little scale notches, and for the x-axis, they're always below the x-axis. That's a convention to know. And this O here is just reminding us that we're dealing with the origin, whose coordinates are 0, 0. All right, example of a good scale, straightforward, easy to understand, nothing fancy in this one. This one is a little fancier, but this is also acceptable. This is also a good scale. Look at this one here. If we look along the x-axis, starting from here from -15, we keep jumping up by +5 each box we move to the right. Right? We keep going along here. The jump between -5 and 0 is the same as the jump from 0 to 5. It's the same as jump from 5 to 10. It's not that I'm skipping to 5 and then making this 6, 7, or whatever, which is something that people often do. Okay? So we got a consistent x-axis. We also have a consistent y-axis. If you look here, I'm at -30. I'm jumping 10 to -20, jumping 10 to -10, to 0 to 10 to 20 to 30. This y-axis is good. It's consistent all the way through. Note here that the scale for the x-axis is different from the scale for the y-axis. That's okay. Even if each jump along the x-axis is by 5, it's all right to have each jump along the y-axis be by 10. You're allowed to do that. You could have each jump along the x-axis be by 100 and each jump along the y-axis be by 0.1. No problem with that at all. This is a good scale. This one's perfectly good. Okay, now let's look at some bad scales. And the bad scales I'm showing you here represent what I'll frequently see as mistakes that people make when they're getting used to scale for the first time. Okay, here's something that I'll see a lot. You see here, like this could be an example. Let's say some guy knows that he has to start putting some points on the graph, and the first point that he knows he wants to put on is the point 5, 5, right? 5 for the x-coordinate, 5 for the y-coordinate. So he decides, okay, well, let me put the point on first and put like a point right here, and then start labeling the axes after that. Right? He'd say, okay, well, now that I've got my point here, let me call this 5, 5 by putting these numbers in on the x-axis and the y-axis. Now, in and of itself, putting a 5 here and a 5 here isn't wrong. The real problem is that this jump here from 0 to 5 is a different jump when I go from 5 to 6, right? This box is worth 5. This box is worth 1. You're not allowed to do that. Inconsistent scale along the x-axis. No good. Horrific. Awful. So angering. So angering. Same thing along the y-axis. The guy's making the same problem, right? Making the same mistake. He's saying that, well, from -7 to -6, I'm jumping by 1. I'm jumping by 1. Whoa, I'm a crazy man. I'm jumping by 5. Watch out, I'm jumping by 5. Now I'm jumping by 1 again. I'm mad. I should be locked up in an asylum. That's what this guy's doing, okay? So don't do that. That's an inconsistent scale. Bad news. Here's another problem that I'll see. In fact, there's a bunch of different problems going on with this one. You might think, why would anyone do this? No, this happens all the time. Okay, see if you can spot what are the problems with this one. Give yourself a second. See if you can spot all the different problems. Okay, so one thing that this guy is doing, and you might assume nobody would ever do this, but it happens all the time, is you see as he's going up along the y-axis from 0, he jumps from 0 to 400, so that's a jump of 400. Then he goes down by 300. Again, he went up by 400, and then he went down by 100. So between 0 and 400, actually 300 would be right here. It's showing up in two different places, the 300. This doesn't make any sense at all. So he's going from 0 to 400, and then he goes 300, 200, like that. People do this all the time, and the reason why they do it is when they run into word problems where they feel like they get used to the idea, well, lines always go like this. The first few problems they tend to be fairly simple, and the lines that they're graphing tend to be lines that go up like that. And so then when they start plotting points, like let's say they have one point that's 10, 400, they decide, well, let me put that point here, and then they have another point that's 11 and 300, which would normally mean that would, like, if 11 and 300 would be a line that's just going downwards as it goes to the right. But they're just so used to making lines go up to the right. They say, okay, well, 10 and 400 is here. Let me put 11 and 300 here, 12 and 200 there. That's how this happens. So don't be that guy, all right? It's completely crazy what he's doing here, but this does actually happen. Another problem, again with the y-axis, is if you look here, as we're going down from 0, the numbers here, these are positive numbers. 1, 2, 3. He's actually increasing as he goes downwards. It's like this top part of the y-axis seems to have nothing to do with the bottom part here. He's just like, oh, these are, two different axes, I guess. No, that doesn't make any sense. Okay? You might say, well, at least the x-axis is sane here, right? He's got -3, -2, -1, 0. Nice, consistent as we're coming along here. But then, even though he's jumping by 1 along here, and even later on here from 10 to 11 and 12, he's jumping by 1 there. The problem on the x-axis is this one jump right here that's just breaking all the rules about consistency of scale. He's jumping by 10. This one box is worth 10. Each of these other guys is worth 1. This one box is worth than all the other ones we can see here put together. So you can't do that. Inconsistent scale along the x-axis. So the x-axis has its own problems, but the y-axis is the one that just goes completely out to lunch and essentially breaks the universe. Cats and dogs living together. Complete apocalypse.